It's a great pleasure to have our joint seminar speaker, special speaker today on Monday, Dr. Cunjiang Yu from University of Houston, to give a talk today. So before he starts, let me give a brief introduction to Dr. Yu. And Dr. Yu is a Bill Cook Associate Professor of Mechanical Engineering at University of Houston, and he also was a joint appointment with a couple other departments, electrical computer engineering department, and also biomedical engineering department. And there was a third one, the material science engineering. I shouldn't forget about that. So Dr. Yu received his PhD in mechanical engineering from Arizona State exactly 10 years ago, 2010. And over the past 10 years, he has really done phenomenal work. So from the title today, you see this fancy word about Rubbery Electronics. So these two words typically not show up all together, but he's putting them together, indicating there are lots of interesting things all the way happening from material synthesis all the way to device structures. So we look forward to hear that. And after receiving PhD from Arizona State 2010, he spent the next 3 years with John Rogers, who is a pioneer for flexible electronics in University of Illinois, and I believe John later moved to Northwestern. And Professor Rogers was also our featured speaker for Sears School Engineering 150 years anniversary. So he was here not a long time ago, and I think today we're going to hear more work in flexible electronics, especially for, it's wrong, I can feel it's wrong, Rubbery Electronics today from Dr. Yu. So due to his work, Dr. Yu received quite a number of very prestigious awards. And just I list a few of them, including NSF Career Award, the ONR Office of Naval Research Young Investigator Award, MIT Technology Review Top Innovator Award, and many others. And I should say that over a past year, 2019, a single year, his work was published in 3 journals in Science Advance and 1 journal in Nature Electronics. So you can see that lots of innovation and large impact coming out from his laboratory's work. So without further ado, I will give the rest of the time to Dr. Yu. Let's welcome him on the stage.
Thank you. Thank you very much, Dr. Zhang, for the very kind introduction. So everyone can hear me at the back, please? All right, great. So I'm going to talk about, as Dr. Zhang also mentioned, I'm going to talk about the rubbery electronics that we have been working in the past few years at the University of Houston. And the title of my talk is Rubbery Electronics Toward the Seamless Integration with Human. All right, so as an engineer, I'm always striving to utilize my knowledge, engineering technology skill set, and device capabilities to solving the great challenges which are facing our society and also the 21st century. So specifically, the great challenge that we have been really looking to or be interested is the great challenge associated with health and joy of living. So in particular, we have been interested into developing devices that understand the human body and also providing therapeutic functions. And simultaneously, we're also be interested into making machines, or sometimes interchange with the word of robotics, that we can make machines or robotics are smarter, that they can interfacing with the human and they can interacting with each other, teaming together, and also making robotics are much safer. So basically make them smarter and safer. So this is also our interest. So specifically why we're interested in that is because we believe that in the future, human and robots or machines are teaming together and the boundary between them becomes very blurred. So this is the reason why I've been working in the challenge of the health and joy of living. So the specific approach we're taking to solving this great challenge, we call it soft curvy electronics. So why? Why we're interested in this soft curvy electronics? This is really placing contact with the development of electronics in the past few decades, especially in the recent few decades that electronics has been entering into our human daily life and has been providing a lot of very positive impacts. For example, there has been electronics that we can create a whole set of implantable devices. And we have the the instrument settings in a hospital that can provide diagnostic and therapeutic functions. And even these days talk about mobile health monitoring and also these biological studying tools, those kind of pins penetrate into the brain tissues, and then they can record and understanding what the neural activities are. All right, so this has been lead to very positive outcomes. Outcomes include the improved health, life quality, happiness, and also has been facilitated the discovery of modern medicine, drugs, genetics, and molecular biology, etc. So you can see it's fantastic. But I can tell you, this also have a lot of challenges when electronics has been interfacing or, merging with a human. So for example, these technologies, implantable devices, sometimes, actually a lot of times, they have incompatibility, immune response to the human body. So body don't like these implantable devices. Or this, instrument in the hospital setting, they are very cumbersome, and also, they are immobilized. To make the patient care or healthcare quality is very challenging. And even these days, talk about the mobile health technologies over here. It's great, mobile, convenient, but it's very challenging in terms of high quality or the correct data setting. For example, the information you acquire, you have a lot of motion artifacts, facts in terms of the quality of data. And also we talk about this biological study called a Utah array. Those pins penetrate the brain. You cause a lot of, especially for chronic issues, talking about the interface between the tissue and those medical devices. So you can see there are a lot of challenges all associated with most of the medical devices. All right, so this is why this problem comes. This is really talking about the distinct nature between a human body biology and electronics. So if you can recognize the human body, which is really talking about whole set of the organs and the tissues, and if you look at the characteristics of those organ biology tissues, then if you look at the shapes, they are curvilinear, and also they are naturally in the dynamic motion settings. And the stiffness, talk about mechanical modulus of these tissue organs in the range of few to hundreds of the kilopascal. But look at the electronics, very different. Electronics, you can see, they're primarily designed into flat and the rigid form factors. And all the electronics function in the static motion. Basically, they don't moving around like a human body. Even they're moving, it's not the way how we're talking about the tissues, relative motion. But talking about the stiffness, the materials associated to making this type of electronic we've been very familiar with is utilize materials, for example, metals or silicon materials in the range of 100 gigapascal. So you can see, for example, talking about the shape, talking about stiffness, significant difference. So try to merge these two together have a lot of challenges. I can give one example. So for example, human brain is the most sophisticated organ in the world, probably. And we try to decipher, understand the neural activities, understanding what's going on. And we're probably going to utilize the most sophisticated artificial device, neuron devices on the world. So basically, the most sophisticated, powerful device is a piece of integrated circuits. All right, so as I mentioned, integrated system made of silicon, this type of materials, and they're very rigid, and you can see also their shape are pretty flat. They're planar structures. But look at the brain tissue over here. They're curvy, they're very soft, like a toothful. So once you immediately try to make these two contact together and matching with or make a good interface, then you find a challenge. So basically, they are not matching with each other. So our hope here is that we envision the future, in the neural electronics, that the devices have the electrical function integrated circuit capabilities, but sometimes they can be conformal and also mechanical, very soft interface, seamless with the brain tissue over here, like this type of setting. And of course, this is not just the one type of device we have been, mentioned over here. Talk about devices that I have been developing my group, devices like smart contact lens devices, like a device sitting on the intestine to do the diagnostic function, and also, device interface beating heart that can simultaneously or concurrently deforming, but while they can do special temporal mapping of the electrocardiographic diagram information. So you can see those capabilities are common feature holding for this type of device is that they're electrical devices, they're bioelectronics, but also they have the feature of softness curvy, which is the feature of biology. So this is we call the softness curvy electronics. This is the reason that we believe that the future electronics should be also soft and curvy to make a seamless integration with the biology. All right. So before I talk about the rubber electronics, then I would like to snapshot and tell you what we have been done in the past few years. So specifically, my group are taking the approach of bottom up, that we have the fundamental technology platform to advance for device applications, or we have the top down, have the application problem-solving capabilities or problem-driven, then we come out with fundamental approaches. So there are, these both interchangeable approach we have been taking in my group. So specifically on the fundamental technology platform side, I call the materials and manufacturing side of this, is that we are actually creating a lot of new electronic material. For example, this is one type of material we have been working. That, for example, this type of electronic material is they're coupled with their mechanical property, has the electrical property. Once they're in a mechanical structure, retain these electrical functions. So basically, converting this material traditionally brittle, but now we can make a piece of rubber. And of course, this is one type of material. We also work on some other materials, the oxide materials, low temperature processing, high density, in terms of ray arrangement. And also, this is, we have been very specialized of picking and place very thin material precisely from one place to the other, which is very critical to making a lot of devices that requires heterogeneous of integration of different materials to make it a function device. So of course, my group also developing, we call a curvy electronics, that approach we call a cast printing. This printing that enabling the development of electronics now traditionally from 2D planar integrated circuits, now we make it the curvy three-dimensional structures. So we have this manufacturing and material capabilities now allowing us to developing devices, for example, like this transistors, arrays, sensors, imaging, integrated circuits in a very flexible version. So we're interested in these devices is because these devices are really enabling a lot of applications in the medical and robotics. For example, on the top frame on here on the right-hand side is a device we've been very interested into developing high-density brain mapping, that you have circuits put into the brain and recording special temperature of the cortex information. And of course, we have on the right-hand side over here is the pins, three-dimensional, but very soft, and then you can have a less invasive in terms of the interface and also the chronic issues in terms of the scar and in terms of the tissue and the pin integrated electronics interface. And we're also interested in this device can see that on the intestine, skins, heart, and also eye. So, for the retina prosthetic. And also we'll be interested in, utilize these technologies that for robotics, for example, this is a robotic skin technology. Robotic skin can immediately, enabling the robots that can interacting with the external environment and then providing, close loop interaction and activation. And this is a softer version of the robotic inchworm devices that can mimic the inchworm crawling on the desk. That can be very useful for a lot of applications in defense and also in medical. And, we're doing a lot of, human-machine interface devices that human and robotics teaming together, and they're forming, augmented reality from the interaction with, of the robotics to the external environment, but give the augmented reality to the human and even diagnostic robotic capabilities. So, specifically what I'm going to tell you today is really from the technology platform development of the rubbery electronic material over here, but we're utilizing this material in a scalable manufacturing way to do the device technologies, and then utilize this device because we'll be really solving the challenge in medical and robotics. So this is what I'm going to tell you today. So now talking about rubber electronics, then we're starting look at the existing type of electronics. This is on the left-hand side is a piece of integrated circuits. So instead of talking about the electrical functions of this piece of device, for example, we're looking to another perspective, looking only the materials associated with this device. So, this integrated circuits were utilized, they're composed of semiconductor materials, of silicon, conductors of all kind of metals like copper, tungsten, dielectric material, SiO2, nitride, those materials, and also a substrate of silicon materials, right? So if you look at the fundamental curve of the strength-stress curve, basically you're mechanically stretching these materials and then look into their mechanical response. And you can immediately find out, this material, for example, some of the ceramic material or semiconductor associated with this integrated circuits that this material, after about 1%, then this material immediately break. It's a fracture. It's a brittle fracture property. And talking about metal, after a few percent, they're actually entering into the plastic deformation, which is non-reversible. And this material, even after 30%, but you can see this material cannot undergo reversible deformation, like a piece of rubber band we have been very familiar with. So these materials, in other words, in short, they're unstretchy. So now, in the past decades, there are a lot of research in the area called stretchable electronics, right? So stretchable electronics is a type of device that they have electrical function, but while they can be mechanically stretched, and even their electrical function can be retained. So there are a couple of device examples here. Stretchable device, and also this device I've been showing before, device sitting on the heart, so you can concurrently deforming with the heart. So now, as I mentioned, the materials is not mechanically stretchy, but you can make a stretchable electronics. So how? All right. So this is I call the architectural engineering. So this is really a practice we have been probably very familiar with every day. A piece of wire, a metal wire, is not stretchy. But now, if you make it coil them up, make a spring structure like a telephone cord. So now you can make it stretchy. So this I call architectural engineering, structural design of this approach. So now we're taking this engineering design, this basic concept, into our engineering design. So for example, we can play with a rubber, and also we have a thin, brittle, non-stretchable material, putting them together by play with the thickness and also the strength mismatch, and then we can create the wavy structures. Right? So this wavy structure is great because like a cotton billow, so that you can mechanically stretch these structures instead of directly posing this mechanical stretch onto this rigid, brittle materials. But now you're changing into tunable wavelengths and amplitude to accommodate this mechanical stretch. And of course, there's a lot of detailed study which talk about the thickness, geometry dependence of this. Basically, it's a very well-controlled way to utilize this thin film and a rubber to make a wavy structure. It's been great. It's been very successful for a lot of devices. And this is talking about Z direction out of plane. But also, you can do the in-plane designs. For example, you can make it like fishnet, like zigzag serpentine-shaped wires. And then you can open up once you mechanically stretch it both directions. So that way you can have the device being very stretchy. So I would say I'll be very fortunate that I've been starting my PhD back in 2007, then studying understanding the mechanics of out-of-plane deformation of these wrinkle structures, mechanical tuning to device applications. And then later on, I studied as a postdoc, then doing this in-plane device design. It's been very successful. The whole community has been, pervasively utilize this approach making devices. Even my group these days, for example, still utilize this device and then to making a lot of device applications. So this is one example that recently demonstrating as a human-machine interface device, which is imperceptible, unnoticeable for the wearer. So for example, here is that we with the device design by very carefully design this mechanical structure to minimize the strain when you mechanically stretch it. But now, sitting on the human body, a skin, then we can record a whole set of data, from transistors as a switching components, memory to record the devices, and storage to physical of the strain, temperature, and also for the chemical biomarkers like glucose, all kind of devices. So utilize this information, health conditioning, physical motion information, then we eventually can build in a closed loop interaction pathway to the robotics. Basically, we make an interactive closed loop human-machine interface devices that, for example, over here we have the robotics that instead of use the human to performing certain dangerous tasks, but we're using robotics. For example, a gas tubing is leaking, catching fire, but we're using robotics to identify, to detecting, and then they perform certain functions. But humans need to make a decision for the robotics. So now, once the robotics are detecting this, interacting with the external environment, so they can send a signal to the human, and the human have the augmented reality that utilizes the on-skin wearable device then to immediately alert the human as the operator to give commands to the robot to form a closed loop interaction path. Of course, you can utilize the signal to control the robotics to forming this. So basically, I want to tell you here is that this is very successful. Utilize this spring structure design to making a lot of device applications and very powerful technology for a human machine interface as one of the example. So one thing, it looks like it's great, but one thing I want to remind you here is one big challenge. Right? So as I mentioned, the device sitting on skin or mechanically you can mechanically stretch this device. It's been great. Macroscopically you stretch this. It's very soft. But once we have the electronics, which we have been really thinking moving forward, that electronics and the organs or tissues or cells interfacing with the electronics, especially the cells, they in the range is a feature size in the range of few to tens of micron. So now the challenge is that the cells are so soft, but they are also so small and cannot see the macroscopic mechanical softness. But only they can see its local mechanical property of these structures, which are fairly rigid in the range of the 100 gigapascal. So basically, there's a mismatch between this intrinsic material property to the tissue or the organs or cells we have been interested. So that's the reason we're really moving on and try to fundamentally use a new set of electronics we call the Rubbery Electronics as we proposed in the past couple of years. So the idea here is that looking at the fundamental curve, but we're instead of utilize this type of material, but looking to utilize the material following this radar curve. So this radar curve is a typical strain stress curve of a rubber. So we hope that if we have this type of material back and forth against stretching, and then we have the materials of semiconductor or conductor dielectric material, we probably can make a transistor integrated circuits. Then we can change the way how electronics really has been provided to us. Of course, human skin is a very good analogy, has been offered us a great inspiration. Human skin have a whole set of sensory organs, feel pressure, you can feel heat, you can feel pain. So all these feeling capabilities are not exactly electrical system, but it's similar. Eventually, your brain can realize it. So what are we thinking that with this type of material technologies and utilize this to build in devices that immediately we can transforming, a device, for example, a robotic hand, then we can give a skin like our human hand. Or the devices can better interface with our human body. So, to creating this type of system, electronics, bioelectronics, so that way you, for example, require the device capability in the matrix to arrays of special temporal mapping capability, analog circuit, digital circuit sensors, integrated systems. So now to create this system, immediately you probably require the fundamental building block. So the building block for this system is a transistor, right? So to make a transistor, then you require this material. A key three materials is to making a semiconductor, which has the rubbery property, and also conductors and dielectric materials. So the material community has been evolving so fast in the past few decades. So we look at how the community has been offered to us, especially looking into these three types of materials have properties. So first material is that the conductor materials. We, look into the literature that there are a lot of options. For example, conductors, you have the 0D of particles percolated in the rubber matrix. You can get a conductive pathway to make a conductive material, rubbery conductor material. You have 1D of nanowire materials, tubes, and also 2D of flakes, and even the option of the organic conductor materials. So basically, you have a couple of options of making these rubber conductors. So what my group has been very interested in the past few years is that we're utilizing these nanowire materials. There are two major reasons of this. So utilize these nanowire materials is because they are high aspect ratio, so they are very relatively long, and a small diameter. So that way, the percolation threshold is fairly low. So that retain a lower amount of the loading of these nanowire materials while retaining the mechanical stretchability. Another reason we're interested in utilizing this approach is that these nanowire materials that we can modify the surface. So it's very critical for transistor devices that we need to interface a good matching between the semiconductor and the conductor to make a ohmic contact instead of Schottky junction. So this is very important. So look into the dielectric material. There's a lot of rubbers readily available, and they are insulating materials. So looks like we have some options like ion gels, elastomers. So what about semiconductor? So once we started this Rubbery Electronics back in 2014, and at that time, you don't have an option. And of course, we've been really working, and recently, a few other groups are also working in these directions as well. So over the years, what specifically we have been developed, I can tell you in terms of rubbery semiconductor, which is the major challenge to creating this rubbery electronics is that, we actually design a material system. We try a lot of options, and eventually it's the organic semiconductor percolated composite eventually work it out. So specifically, the material is the double penetrating network. This dark color of this nanofiber structures, they're interpenetrated into the rubber matrix of polydimethylene siloxane, these materials. And then, look into these network structures, and you mechanically stretch these structures, for example, up to 50%. We do observe a lot of, these connections, after mechanical unit actually stretching, but still you retain a lot of connection to allow the carrier to hopping through from one fiber to the other. Eventually, you can retain the semiconductor properties. So we come out of the way and, to process the material by using a cooling assembly, induced assembly process, and then to create this material. So if you look at the microscopic of this material, and this bright color represents this nanofiber structure over here, and this material, you can see it's a really percolated, and this is a 10% of mechanical stretch unit actually. This is a 30 and 50%, and we do observe some of the disconnection sites or breaking of the nanofiber structures. But overall, based on our device evaluation, these nanowork materials are still percolated, are connected with each other, allow the carrier from one end to the other, which is very important for electronic transistors, right? So microscopically, this material is rubber, so you can kind of stretch, twist, all kind of mechanical deformation. This is indeed our first generation of this rubbery semiconductors. But one thing I want to really remind you here is that we're not just making one small amount of materials, making one device. Our goal is to making integrated electronics. We need to have a scale manufacturing capabilities. So now, we utilize this material manufacturing approach. Based on this solution, we create a scale manufacturing in terms of, for example, in the solution phase, we talk about this assembly and the cooling. Induce the solution, we can do all kind of printing process, which is scalable, right? And move on with this is our third generation of this material that we even creating more scalable manufacturing, roll-to-roll manufacturing to allow scalably manufacturing these materials, and then we can create in devices. Utilize this the air and liquid interface assembly. So for example, in detail, this type of material, we're creating, actually, this is the phase diagram map of this material by putting this two material system, but now we utilize this morphology. For example, we carefully design this material into certain, a mixing ratio, and then we can create a phase diagram map, then allow this morphology of this structure become a network structure. So this network is mechanical property, very beneficial. They can be mechanically stretched, right? So, we optimize their mechanical stretchability and also the device capability in terms of mechanical stretching, how their electrical carrier mobility are going to be degraded. So basically, we utilize this, we can try to find a best option of these materials. So the take-home message here is that we find out about 65% of polysilicon materials, the organic semiconductors, mixing with the rubber, small plastic rubber of the SEBS. Then this structure can be mechanically of these network structures and allow the mechanical stretch, and then you can retain pretty good device performance. So the take-home message here is now we have knowledge to create the rubber semiconductor materials. All right, so the test bed of this, utilize them to create a transistor. So for those, if you're not very familiar with the transistors, I can give a very So, this is a water faucet. So water faucet, so it's a mechanical device that using the mechanical turning the knob. So basically, you use a gate and then control the water current between the source and the sink, right? So transistor is a device, is a nonlinear electrical device similarly, but you use the electrical voltage of the gate. And then you can tune in the source and drain current So this electrical engineering, this electrical device, that now everything are made of piece of rubber. So then you don't need to create any spring structures, and you can mechanically stretch. So basically, this is a rubbery transistor, and this is we really care about the source and the drain, and in between the channels of semiconductor materials, and look at the device characteristic of transistor that you basically need to switch on and off. So basically, you have a current modulation. So by applying voltage. So from this curve here, you can see the black curve is represents the transfer curve that utilize VG. Then you can just by apply 1 or 2 volts, you can modulate the source and drain current by a few orders of magnitude. And more importantly, that this device you can kind of stretch along different directions. This is a channel length direction, and you can stretch about 50%. The device semiconductor nonlinear the transfer capability of the gate modulation is still preserved, and also you stretch perpendicular to the channel length direction, you still reserve by 50%. And we do carefully look into the carrier mobility of these materials, and we do observe some of the degradation, about 40 to 50%, after about 50% of uniaxial stretch, which is expected because we do observe these nanofibril disconnections after mechanical stretch by 50%. But the message here is this device still function after 50%. They still have the transistor property. So we're being very excited about it. This is our first generation of the transistor working, and we feel like probably we can do more. So we're being very excited, and MIT Technology Review has been also interested in highlight the work. But one thing I want to mention, make a transistor really work, make integrated electronics. You really want to have the device are working in high performance. So in terms of high performance, one caliber is you need to use a high quantity of material. One measure is the mobility, carrier mobility. So we want to have the high mobility of this material. So previously, our first generation material is using 2 material systems, double penetration network materials. The mobility is about 1. But here we really want to boost it. So how are we going to boost this material? How are we going to boost the mobility? So basically, we're introducing the third material. So the third material approach is that we're actually incorporating metallic carbon nanotube on purposely to enhance the mobility almost by 10 times. This is our second generation of the semiconductor material. So why? It's because we're utilizing this metallic carbon nanotubes. It's because very high carrier mobility through the metallic carbon nanotube. But also, they actually providing the fast tracks, but have a good interface with the semiconductor materials. So we utilize these metallic semiconductors, high mobility, and also the work function match with the homo level of these organic semiconductors, nanofiber structure, then to allow the carrier to easy flow. So, utilize this, we have the 3 material system. Now we can design, optimize the composition of the metallic carbon nanotube. So for example, we can put more metallic carbon nanotubes. Then you probably end up with shorting the source and the drain. You sacrifice the off current or the off ratio. So basically, we create a way. We come out a way to incorporating this metallic carbon nanotube by physical fabrication methods to incorporate into the previously fabricated this 2 material system. Now we can adding third material, metallic carbon nanotube, and we can optimize the amount of the metallic carbon nanotube into the system, and also look into the on-off ratio and the mobilities, and we can do the material optimization. So here, the optimize is that we utilize the 0.05 weight% of metallic carbon nanotube. We can achieve the mobility by 10. So basically, you're boosting from 1 to 10. And again, we're creating not just the one transistor. Mostly we're interested in that to have the integrated electronics means you have a lot of devices. So now we're using device arrays to evaluate the repeatability and also the reliability of this device in terms of fabrication, in terms of device performances. So you can see this is a device array, and this is a mapping of the mobility. So fairly good in a fairly large array of devices. And everything here is you don't have a rigid component, you don't have silicon, but now you also can mechanically stretch. You can stretch, you can kind of bend it. It's everything made of piece of rubber. And still, we do observe some of the degradation, but it's still tolerable depending on your device application. So now, it's great. You have the device transistor array technologies, integrated electronics. But, if you look at our computer or phones, right? So these electronics are working not just the stacking of this transistor, but they're working on 0-1 digitized operation. So now, can we have this digital logic gates that also based on the rubber transistor, everything made of piece of rubber? Answer is yes. We do have creating this inverter. You input 1, you get a 0, or you input a 0, you get a 1. This inverter logic gates and everything made of piece of rubber. And this is the device characteristics. So, and also we do the NAND gates and the NOR gates. So basically talk about digitized operation of these devices. So here the devices, after a mechanical stretch, for example, by 30%, the device, the truth value of the logic gates still preserved. So now it's the first time we have this capability of digital logic gates, but now it's fully rubbery. All right, so great. Everything I've been showing here is based on our polysilicon. So polysilicon is a P-type material. It is very challenging that you're going to have N because we already know that the transistors, their circuits are working at the P and N. We call it complementary, CMOS. So CMOS device, you need to have P and N, but now everything I'm talking about is talking about P. So in the past about 2 years, we have been collaborating with the Northwestern University Tori Marks and Antonio Facelli group. They spin off a company talking about this material called N2200. This is an N type of semiconductor material. We have been really working and making a rubber version of this. So now we can have the CMOS, complementary rubbery electronics. Then we can have the digital logic circuit. We have the analog circuit design and device capabilities. So because of time, I probably are not going to show much detail. So now the message I want to deliver to you is then we have a whole library of the P and N. We can do integrated electronics. And of course, the number in terms of digital logic gates, then the number of transistors are fairly low. We're just a few tens of transistors. But what about hundreds? What about thousands? What about even up to more? So then we still really working on to pop them up. Eventually, we really can converting a piece of glove we're wearing in the laboratory to a piece of integrated circuits, high-level integration of the electrical functions. It's been great. We have this transistor integrated electronic capability. But one thing I also want to remind you here is the semiconductor material, rubbery electronic materials of conductor dielectric material can create sensors. And especially those sensors are very beneficial for large mechanical operation zone. So for example, over here, we can create the physical-based sensor like a strain, pressure, temperature sensor. Based on this two-terminal device architecture, utilize the semiconductor sensing elements. Then we can create this device by mechanically stretching them. You can get a really fairly linear response of the resistance chain depending on which direction you're going to stretching. And also you can get the device response more cyclically in a repetitive way. So this device can sensing the mechanical stretching or strain. And if we're comparing our device with the most commercial available device, the talk about the gating factor here is the sensitivity of the strain sensor, which is the relative resistance change over the strain you applied. So that is a gating factor. Talk about sensitivity. The best of this is the light P-type doped silicon. So this P-type silicon is the highest gating factor of 200, but you can see silicon is a brittle material. So the operation zone is about 1%. Then the material eventually going to failure. So you only can apply to these cases are very tiny mechanical strain. So the most accessible strain sensor is based on metal strain gauge. So the metal strain gauge has the operation zone of 5% because the elastic zone of these metals. But the gating factor is in the range of 2 to 5. So it means you slightly increase the operation zone, but your gating factor sensitivity is much lower. So in our material, our first generation of semiconductor material, what we have been achieved in the range of about 30 gating factor, and a fairly linear over the range of 50%, which is very important for sensor technology. And further optimize this material, we can even achieve more than in the range of 100%. Then we can preserve about 20 to 30 gating factors, which is very very interesting, especially for a lot of applications that associated with very large mechanical deformation of 50 or 100%. All right, so because of time, I'm not going to show those details, but I want to also emphasize here, similarly for the pressure for temperature sensors. Utilize this material system, now you can significantly expand the operation zone of this sensor technologies. And with this sensor technology, immediately, for example, you can, allow the robotics, say, to sense the temperature, for example. You equip the robotic hand and with those sensors, even associated with large mechanical deformation, for example, touching object, they can immediately, in situ monitor their temperature. And also, utilize this robotic hand, then we can translating, because the finger joint is large mechanical deformation, use that, we can translate the finger gestures. For example, American Sign Language is very hard for me, for a lot of common, typical people to understand. But, with this equipped large deformation of the sensors, so then we can directly translate the finger gestures into readable letters. So then you can create a communication pathway between the performer, either a person or robotics, to performing this American Sign Language to a person who can read it, understand it. So this is one of the examples that, a lot of deformation, for example, in robotics applications that we associate with large mechanical strength, but now with our sensors, you can do a lot of capabilities improvement. So I'm talking about sensors, but I'll tell you one challenge in the sensor areas, especially, skins for robotics. So one thing, the challenge here is that, it's great you have, few sensors equipped on the robotic skin or equipped on the arrays of the smart skins. But eventually, like our human skin, once you touch it, you have innumerable number of sensing nodes. So now, how are you going to create not just the one, but you have hundreds, thousands, and more in a small, fairly small footprint. So if you're doing individual wires, you probably end up with very fuzzy interconnection wires, then make the system really doesn't function. So here is, we really want to create a skin, but here we call utilize active metrics. Using the transistor technology working, they really can helping us to have the high density spatial temporal mapping of the sensor capabilities. So basically, you're trying to merging the transistor technology with the sensor that can give you high density of array of the devices. So in particular here, I want to show here is a tactile sensor skin. So this tactile sensor skin, everything made of piece of rubber. So you have the pressure sensitive rubber. This pressure sensitive rubber, once you press it, the electrical characteristics like a resistance change. And everything over here, you have the transistor active matrix arrays, and everything made of piece of rubber. So now it's a fully rubber system. But if you look at the array and look at the individual pixel of this device, right? So we have flowing a VDD to the GND through this pressure sensitive rubber and the tactile sensor sensing elements, but passing through this active matrix transistor multiplexing, and then you can eventually going to go to the GND, to the ground, and passing through a shunt resistor. So using multiplexing technology, then we can recording the voltage on the shunt resistor of R, then we can know the voltage occur because when changing the tactile sensor, the resistance change, and then the current change, and then the V out change. So based on V out change, we can back calculate how mechanical touch you apply, and then we can know the tactile place and the pressure. So using this concept, then we can multiplex and do a special temporal mapping of this device technology. So now everything is made of piece of rubber, so you can kind of stretch, and even when you stretch it, we apply a weight on this skin device, and they can still resolve even after mechanical stretch about 30%. So now, great. So you have this active matrix sensing array skins. So you can immediately, enabling a lot of applications in robotics, for example. But one thing, for the smart skin or, robotic skin here is that the skin, like our human skin, right? Once you touch it, your brain can feel it. So how that works, right? This is really talking about the neuron, right? Neuron transmission, communication from your skin to your brain. So I can give an extreme case, right? So for example, I have a hammer to strike your knee, and then you basically realize I have a response to it. So what's happening? Neuron connection pathways. And how neuron to neuron communication is neuron synapse. So one thing I want to emphasize here is that neuron synapse, usually we don't observe, but actually in human, like a spinal cord or peripheral nerves, they're actually mechanical stretching. Even we don't do that. A lot of neurons, peripheral nerves in the skin, the tissue, they can be mechanical stretch. But I can use one extremely case, for example, an inchworm. Earthworm, inchworm, you can extend or elongate their body by a few times, and their neurons still functions. They still can perform the function. So one information here I want to show is, basically the neuron capability, neuron functions in the skin can be mechanically deformable. So now we can create a neuron device. So what we want to do is that eventually can equip the neuron function capability like our biological human skin, then we can have the neuron functions into the smart skins over here. So, neural synapse is really an interesting function that we can give the presynaptic pulse, and then we can generate or yield a postsynaptic current and potential based on the neuron transmitters. So this is really similar to like a transistor or a synaptic transistor device that, we have use the gate by modulating a presynaptic potential, and then we can modulate the source and drain current. So this is the device architecture we have been utilized for, first generation of these devices. So utilize the gate voltage spots, and then you modulate to give a postsynaptic voltage and a current. So if you look at the device function mechanism, we have a gate here, and this has this dielectric material over here. And once we apply a pulse, so the number of carrier in the source and drain, the transient response. So basically, you increase the pulse, apply a pulse to the gate, and then you're actually mirroring the charge and injecting into the source and the drain. And now you actually get the postsynaptic current. And if you have successive, like second pulse, and then you injecting more, and then you have the memory effect by stacking the transient response of the ion in the source and the drain, and then you have the memory effect, short memory and long-term memory. So basically, we based on these device technologies, we can create a device are fully rubber, and then they still have the memory effect capabilities into these devices. So now we have neuron capabilities in the rubbery concept of form factors, and then we can immediately integrate to engineering or smart skins. So for example, here mimic the human skin. That human skin once you touch it, your somatic sensing capability can generate a presynaptic voltage, and then you actually activate the neuron and eventually let your brain to realize. So what's happening in our engineering device is that we have the rubber-based mechanoreceptor. Once you touch it, you actually generate presynaptic pulses, and these presynaptic pulses will activate this synaptic transistor devices and generate this postsynaptic pulses or currents. So this is a one-channel device operation. So we can do the array of devices. You can do the mechanoreceptor. Once the mechanical press, you generate the spikes, and use the spike, we can generate the postsynaptic mapping. And mapping of that, so this device eventually can directly building a neuron pathway from the neuron device of the smart skin to the biological neurons, which we have been really working culturing these neurons, and we mechanically kind of touch and scratch this skin. Neurons can be fired. So this is some of the results which haven't published yet in terms of how the neuron to neuron interaction, but hopefully in the next couple of months, we're going to show some of the interesting results of that. So, we have the neurological function integrated devices. But one thing we probably immediately also be interested in is that can we create another class of devices? For example, robotics. Now, robotics, like a soft robot over here as an example. Soft robotics, the robotics performing for example, the crowning motion, right? The deformation motions, or based on the operator, the commander, give or tell them where to go. So now we hope, can we allow the robotics that have a similar mind or thinking capability in our human or animals, even in a very simple way? So how? So it's a neuron function. So basically, we utilize this neurologically integrated function of the skins and implement it to a robotics. So now using neuron decoded signals, for example, based on number of touches. So then this neuron decoded signal can immediately to let the robotics to perform, for example, walking or turning angle of directions that to make them more smart. Of course, this is just one step of this, and really make them truly smart, get a trend, and then you need to have the more sophisticated device. But this is the first step. Then we hope that the future, the robotics we call the neural robots. It's not just a neuron device, but eventually they're probably going to have some of the thinking intelligence capability in our human. All right, so everything I've been showing here, I talk about neuron devices, and my starting point is really these devices can talking about the the seamless integration with the biology, with the human tissues. So now I want to tell you one example, but which my group has really moving into a lot of bioelectronics, talking about the neural interfaces. So this is an example of the cardiac device. It's an epicardial on the surface of the heart. So this is experiment done with the Godian mini pig. So this device here we show is a bioelectronic, but it's a patch device that you have the transistor technology, active matrix, that this device actually sitting on the beating heart like this and concurrently deforming with the heart without posing a lot of mechanical constraint on the beating heart. But now you can simultaneously to do the 3D or deforming the format of the heart to the special temporal mapping of electrocardiogram. So basically over here, this is the ECG, and then we're mapping the R signal peak over here in real time. So now based on understanding the ECG mapping, then we actually eventually can know not just the ECG signals, but also how the signal propagate along different directions to identify some of the arrhythmia problem in the heart, which is very critical. So, we created this device. Actually, cardiologists get very excited about this. They're opening up a whole set of diagnostic capabilities. And of course, as the Rubbery Bioelectronic concept, we also integrate some other functions into the system. So we have the physical, we have the strength sensors, then we can monitor a normal beating, and also, the pacing of the heart. And we have energy harvesting, so basically using the tribology technology concepts. Then we actually have the rubber concept, and then we can harvest the mechanical beating and into electric energy, and with the hope that eventually we can save them, harvest them, and then to make a sustainable system. But this is just a standalone energy device so far. And also we have the temperature sensors, thermal actuators to do the thermal ablation once we identify a problem and want to externally to intervene this problem to change the conduction status of the heart. So this is one example of the bioelectronic. We have more and more, bioelectronics are going on. So here, because of time, I want to summarize and hope to convince you that this is what we have been developing so far of the rubber electronics. In particularly, I want to summarize with providing a roadmap. So this roadmap is really placed in contact with the last century back from the 40s that people recognize the importance of black silicon, and then late 40s of discovery of the nonlinear electric device called a transistor. And this transistor has been named to early 60s of Texas Instruments talking about integrated circuits, and then these days are of course talking about large scale integration, very large scale integration, or ultra large scale integration, ULSI. So, in the past few years, starting in 2014, we started this, try to work with Dartmouth. So we really have been developing materials that, has been creating rubbery semiconductor material, the key material to enabling these transistor integrated electronic technologies, to making transistor, to, this circuit digitized operation, and to a number of integration. And of course, the level of integration is not comparable with VOSI yet, but hopefully we can keep moving on along this direction. And immediately we can find a lot of applications which are very unique that rubber electronics can play an important role, talking about robotics, talking about the bioelectronics, especially we've been really working on in the past few years. So with that, I would like to stop here and acknowledge all the work has been done by my students, my postdoc or former postdocs, and also my collaborators talking about animal experiment at the Texas Heart Institute, and also my funding sources. So with that, I would like to stop here and happy to take any questions.